Now, let's talk about acceleration. We want to be able to define it and we want to know how to calculate it. Now, um, we learned that velocity is a vector quantity, and that means that it has how fast and which way. So many meters per second in the positive direction, or so many meters per second in the negative direction, or to the north or to the west, what have you. Um, and that velocity we know doesn't account for the entire state of motion. So, for example, if a car starts at a traffic light and it's not moving, so it is at rest, not moving. And when the light turns green, the car begins to speed up to the right. And sometime later, the car has a displacement and a velocity. Um, so it's moving faster, or at least fast, to the right. Well, then that velocity changed because over here the velocity is 0 meters per second. Then the light turned green and the car sped up to the right, and over here the velocity is not 0. So the velocity changed. Right, from the instance on the left to the instance on the right. And if we took a look at that at each point on the trip between where it started and where it ended up, say if we looked at the velocity here and here and here, then it's different. It increases each time we look at it. It's greater and greater and greater. Now, that change in velocity and how fast that change happens is what we call acceleration. So acceleration is the rate of change in velocity. And rate means per second or per unit of time. So if anything is a rate, it is something over time. So this is the change in velocity over the time. Now, when we learned displacement, we learned that displacement was the change in position, where this delta meant change and this x meant position. So if I want to do the change in velocity, then that is delta v, the change in the velocity. So the rate of change in velocity, acceleration, is the change in velocity over the time. Well, that change in velocity, this delta v, the way that you figure out the change in velocity is you take the final velocity, so the little f means final, right? V with a little f, velocity final, so v final, and you subtract from that the velocity at the beginning, or initially, vi, and that means initial or beginning velocity. So the change in velocity is v final minus v initial. That's the velocity at the end minus the velocity at the beginning. So to find acceleration, it's v final minus v initial divided by t for the time over which that change occurred. Now, this is how we calculate the acceleration. V final minus V initial over t for the time. So the units for acceleration, well, we know that the units for velocity are meters per second. And the units for time are seconds. So if you look at this equation, this is velocity on top over time. All right, so it's velocity over time. That means it's meters per second per second. Now, I know this is not how mathematics works. If this were a math problem, say we had a fraction divided by a whole number, you know, we would invert the we would invert this numerator and multiply. Well, that's not what we're doing here. Here, what we're doing is we're just saying that acceleration is the change in meters per second every second. Meters per second per second. Right? So this is a mouthful, meters per second per second. So we just decided, hey, we're going to call that meters per second squared and let this be the units for acceleration. So if you were told that an object has an acceleration, for example, of 2 meters per second squared, then that would look like this, 2 meters per second squared. These are just units. You don't square any number. This is no different than saying, hey, the distance was 2 meters or the speed was 2 meters per second. You know these are just units. Well, these are the units for acceleration. Meters per second squared. They're just units. You don't mathematically square any number. But hopefully you see why we shortcutted this mouthful and just decided, hey, we'll call it something different. Meters per second per second. How about meters per second squared? And we move on. All right, so here's how we calculate the acceleration. So let's practice a couple of these. What we want to do when we read a problem and we want to find the acceleration is identify what's the V final, the velocity at the end, and what's the V initial, the velocity at the beginning. Then we'll take the difference and divide it by time. So here's the first problem, and if you would like, you can pause the video and calculate this acceleration, and then we'll work it together. Okay, so a car is moving with a velocity of 8 meters per second and it speeds up to 16 meters per second in 8 seconds. Well, this was the speed it had at the beginning, so that's V initial. And this is the velocity at the end, so that's V final. And of course, 8 seconds is the time. So now all we need to do is use our equation. Acceleration is V final minus V initial divided by the time. So I see that my V final is 16 minus the V initial, which is 8. And we're going to divide whatever that is by 8 seconds, the time. Well, 16 minus 8 is 8 over 8 seconds. That's 1. And since this is acceleration, the units are meters per second squared. That's the first practice problem. Find the initial velocity, the final velocity, and the time and you can find the acceleration. Now, this is actually an average acceleration from over this 8-second period. In the beginning, the acceleration might be very low. The rate of change in the car's speed is very low. But with time, it might speed up quicker and quicker and quicker. So when we do this, this is actually an average acceleration over that period of time. And later on, when you learn a little bit higher level of math, we'll be able to look at systems where the acceleration is not constant. We don't have to use averages. Okay, let's do one more practice problem. So this one, a car is moving at 24 meters per second. It slows down to 12 meters per second in 4 seconds. Find the acceleration. Okay, looks like it was initially moving at 24. It slowed down to 12, so its final velocity is 12, and 4 seconds is the time. So acceleration is v final minus v initial over the time t. So the final velocity was 12. The initial velocity was 24. And the time is 4. Okay, well 12 minus 24, that's a negative 12 over 4. 12 divided by 4 is 3, and this is negative. So negative 3 meters per second squared. So here's the acceleration, and here's what it means. Velocity is a vector, and you know that displacement is a vector. Acceleration is also a vector. And in this case, if you look at the first practice problem up here, for example, the velocity is 8 meters per second. Well, velocity is a vector. It has to have a direction. I gave you the direction. That's a positive 8. So if you just think of a number line, like an x-axis with negative going off to the left and the positive numbers going off to the right, I just said that this is moving to the right. That's positive 8 meters per second. All right, and it's sped up to a positive 16. Well, if you look at our second problem down here, this is a positive 24 meters per second, so it's moving to the right. In order to slow down, its acceleration had to be in the opposite direction. So if a car or any object is moving to the right, if its velocity is to the right, that's positive velocity. If its acceleration is to the right, that's positive acceleration. That will make this thing speed up. That's the first practice problem that we just did. It sped up because it was positive velocity and it had a positive acceleration. And if the velocity and the acceleration are both positive, which means in the same direction, then it will speed up. In the second problem, we had positive velocity, that's moving to the right, but the acceleration is negative. That means the acceleration was in the opposite direction. This means it will slow down. All right, so acceleration is a vector. Its direction matters. And now we know how to calculate it, and hopefully we know what it means to have this positive acceleration in the first example and this negative acceleration in the second example. Now, if we really wanted to get complicated, we could say, oh, an object might be moving to the left, in which case it would have negative velocity, and if it had acceleration also that was negative, it would be speeding up in the negative direction. All right, up here, this one's the first example, speeding up in the positive direction, slowing down in the positive direction. Okay, this third example here, speeding up in the negative direction, or we could be moving to the left, that's negative velocity, and have positive acceleration, which would mean we were slowing down in the negative direction. Right? So this is what it means to be a vector. The direction matters. If the velocity and the acceleration are in the same direction, something will speed up. If they're in opposite directions, it will slow down. Now, often we use the word deceleration. That just means slowing down. That means that the acceleration and the velocity are in opposite directions. Okay? Okay. I think that will do it. Yeah, that's good.